Hello, this is Ahmad Numan Khan and I am going to present an IoT-based solar panels testing system that was done under the supervision of Dr. Nabil Siddiqui as our final year project. The group member is me, personally Ahmad Numan Khan, and my mate, engineer Afaq Hussain. Starting from the contents of the slide, it includes introduction, motivation and problem statement, literature review, objectives, methodology, results, discussions and the findings, and ends with a conclusion and future directions along with references. Now, as an introduction, about 3% of the world's electricity comes from solar. The biggest contributors among this 3% include Bhadla Solar Plant in India, Hungai Henan China, Shakti Sthala in India. So, overall, solar power plants consist of huge arrays that are distributed in series and parallel. Coming to that, talking about motivation and problem statement, the major motivation behind this project is that about 60% of power generation in Pakistan relies upon conventional means, such as thermal power plant. The same is the case with numerous other growing or developing countries where the power production is widely done via conventional means and we need to switch to the renewable means. So, talking about that, the major problem statement that we have is that solar power farms or solar power plants are spread over huge areas, like Bhadra solar plant covers 160 square kilometers. Now, a series of single solar farm may contain up to hundreds of thousands of PV panels. Technicians, when they come for resolving a problem, they first have to find out which solar panel in a whole series is malfunction. And for this testing, they have to check each panel individually, which is a huge time-consuming process. Now, to solve that, we have come up with a design. We'll be coming to that. About literature review, the researches presented till now focus solely on monitoring via IoT. Different methods have been used to connect solar panels to the internet. So what we studied till yet, there are some papers that we are going to present here or talk about. The first paper that we studied was Smart Monitoring of Solar Panels Using Amazon Web Services by Ravi Kishore. And this method used Amazon Web Service as the cloud computing, or you can say as the IoT means. Next, a few other papers included a paper of Mr. Zahran about LabVIEW-based monitoring system, a paper about Zigbee-based data acquisition, and an integration of Blink for domestic usability paper by Hiral Doshi, Minesh Shah, Umair S.A. Sheikh. And this paper was the one that gave us major help in our project because we have also implemented integration of Blink. Now, talking about the objectives, the major objectives of our project include to strengthen the bridge between IoT and solar energy industry, to inspire automation in the solar industry, to find a low-cost method for solar panel testing system, and to research new methods of solar panels remote testing. Starting from Internet of Things or IoT, that is the major portion of our title of the project, IoT-based solar panels testing system. What is IoT? IoT is basically a network of things, sensors, motors, equipments that communicate with each other through central communication device or what you may call the internet. So why have we chosen IoT for our project? The major reason behind that is that it allows us remote control. It allows us for automation. It enables us to implement smarter methods of connecting devices, and it also gives us a wireless connection system, and that means lesser electricity costs and more cost cutting. So another major thing about IoT is that for aiding IoT in any system, we must aid a communication device that can connect to the internet and an internet server, or what you may call as a database. So for our project, what we have used as the communication device is the Node MCU that you can see on the right hand side of my screen, and the Blink server that we talked about earlier and that you can see on the left side of the globe that is presented on the screen over here. So this whole integration of Blink app with Node MCU and the solar panels on the other hand give us a complete IoT based system. Talking about the methodology. The methodology includes using ESP8266, which you may also call as the Node MCU. It also includes some relays and Blink IoT for connecting hardware to the cloud. Now, we used a several steps-based system to reach to the final results of our project. The step 1 in our method was reading sensors data from ESP8266. Because we are using two sensors, one is the current sensor and other is the voltage sensor. Because any testing system for solar panels includes two major tests. One is short circuit current test, other is open circuit voltage test. We'll be coming to that very soon. Now, about the reading sensor data, it is not a simple process because the current sensor works on Hall effect. If you're wondering what Hall effect is, you can see in the blue box in the right hand side of the screen that it is basically an effect that comes in the form of a potential difference and produced across a conductor when a magnetic field is applied in a direction perpendicular to that of the flow of current. So when we give our current sensor a potential difference or current passes through it, another potential difference is developed horizontally across this, due to which there is some difference of the overall measure. So this induced voltage depends upon the sensitivity of the current sensor. The sensor that we have used, it has a 66 millivolt sensitivity, or what you may say a 0.66% sensitivity. It means that if 1 ampere of current flows through our current sensor, it will induce 66 millivolts on the opposite ends as the Hall's effect. So that the final reading we get from our current sensor is taken from the formula that ADC voltage, which you may call as analog to digitally converted voltage coming from the solar panels, minus offset voltage. Offset voltage is basically half of the voltage that is given to the current sensor, because current sensor is a passive device. It cannot work on its own. We have to give it some potential difference in order to work. So the formula is ADC voltage minus offset voltage divided by sensitivity. Now, the same approach is used in voltage sensor reading. However, it is a bit different because voltage sensor does not work upon Hall's effect, and instead it works upon the voltage divider rule. Now, what is voltage divider rule? All the engineers know about it, and it is also mentioned there in the blue box in the lower right corner of the screen. So, as per this, there are basically two resistors fitted inside a voltage sensor. When a voltage arrives at the voltage sensor, it is divided among both of the resistors. The voltage sensor that we have used has two resistors. One is 7.5K and the other is 30 kilo ohm. So when a voltage comes, or when a voltage is given to the voltage sensor, a portion, or what you may say is 75% of voltage, is induced at the 30K resistor, while 25% is induced at the 7.5K, or what you may call division of voltage. Now, talking about the methodology, step 2 initiating short circuit current and open circuit voltage test. As I said earlier, these are the two basic tests that we conducted for solar panels testing system, and we enabled it or made it IoT based. Now, this is an image of the practical circuit that we created. In this, you can see the node MCU on the breadboard in the black color. You can see a 4 channels relay module. You can also see the current sensor and the voltage sensor. So there are basically 4 major components being used over here. Talking about the short circuit current test. Short circuit current test is basically taken by shorting both of the wires of the solar panel. Or what you may say that by connecting both of the positive and negative wire of the solar panel into the multimeter. However, when the same approach is observed via the current sensor, the methodology differs a bit. As you can see over here, there is a significant change of circuit. On the top left side of the current sensor, a black wire is directly going into the node MCU's ground, because that is the ground wire. A blue wire is directly coming to the node MCU's VCC slot, which you can see in the second slot or second pin of the node MCU. And the central wire is our major wire through which the reading is taken. And the central green wire is given into the analog input, or what you may call as a node pin. Next, talking about the open circuit voltage test or short circuit open circuit voltage test is basically taken by pretty much similar method. The only difference over here is that there is no central wire going from the voltage sensor, because no voltage is directly induced on that common pin, and instead we take the complete voltage from the very two ends of the voltage sensor. The black wire that you can see coming out of the voltage sensor is directly grounded, and the green wire that you can see is directly given into the analog input area. You will also see that basically, as I mentioned, there are two resistors in our voltage sensor. One is 7.5K and the other is 30K. So this green wire going into the analog input pin of the node MCU, this represents the 7.5K resistor. We had chosen this because we needed lesser voltage reading over here. Now, talking about the step 3 of methodology, sending sensors data to the cloud. And our cloud is Blink. Blink is an IoT platform that not only provides a cloud database, but also helps develop iOS and Android application interface to control your IoT-based home appliances or similar circuits via Node MCU ESP8266. So this was the best part of our project, because Blink Server enables us to use the Node MCU right away. We did not need any other integrations or any extra equipment to communicate or to enable the Node MCU to communicate with the Blink, because Node MCU already comes with a built-in Wi-Fi system. So what happens here, which you can see in the picture on the right hand side of the screen, is that voltage and current readings are taken into the Node MCU. Those readings are transferred via the internet and the Blink libraries to the Blink server, and then those readings are presented into your Android or iPhone iOS application. Talking about Blink interface, when you log into www.blink.io, you'll come across this interface after creating your user ID, where you can create devices. This is a practical interface picture of our device that we had created. So you can see quick start in the my devices section. You can see the name of device owner, which is myself, and you can see the status that it was offline at that time. When we turned it online, the status would change because whenever the node MCU would be connected to the internet, it would show online. This is another image of the Blink web interface where you can see several tabs such as info, metadata, data streams, events, automation, web dashboard, and mobile dashboard. We have opened the data streams tab, and you can see in it several pins that we created. You can create a lot of pins in this web interface according to your use or your requirements. The pins that we created, as you can see, include voltages, voltage relay, current relay, load relay, current, and several others. Now, this is an image of the actual Android interface of the Blink. As you can see on the right hand side of my screen, right below my image, there is this Android interface of the application that we had created for a single panel IoT-based testing system. You can see voltages and current readings. You can see 3 push buttons. They are currently in off state. Whenever you push them, they quickly switch into on test, and from the button that is right below the voltages, voltage test is conducted. From the button that is right below the current tab, short circuit current test is conducted. And from the central off button in the below section, the load is connected directly with the MCU. So this is an image of sending sensor data to Blink. How do we send sensors data to Blink? How does our node MCU knows which programs or which functions to conduct? And how does it change or converts the voltage and current readings that are read from the sensors? Everything is done via programming. And this is an image showing some portion of the code that we wrote. There were about 6 to 7 more pages of code, and of course a lot of variable declarations that are made over here. You can see the comments as well, such as the 4th or 5th line saying v in variable declaration, register of voltage sensor, and similar others. Now coming to the step 4, that is implementing for 4 panels in a series. Now 4 panels in a series, this is also a part of our project because overall this was the major part of our project. When there are 4 panels in a series, we have to make it automated enough so that the tests are conducted IoT based without having to disconnect each panel on your own. So this is the tested circuitry you can see over here, and there are 4 panels all connected in series. However, the wires of all 4 panels are going into a 16 channels relay module. There is a node MCU as well as a 5 volts battery connected only to power up the relay module. This is the Blink configuration for the 4 panels in a series form, but this is not the complete picture because there are so many pins. Overall about 25 pins that we had created in the Blink interface so that our 4 panels in a series test can be conducted fruitfully. This is Blink Android application interface, and now you can see the interface is a bit different because it is for 4 panels in a series. Now there are 4 push buttons, one for each panel, first for the first one, second for the second, and so on. You can see the voltages and currents. Whenever you push a button, the voltage of current of that specific panel will be displayed over here. Talking about the programming for 4 panels, this was a major portion of the project. where we had to program our node MCU or ESP8266 in such a way that the result is fruitful and the test is conducted properly. These are just two example images of the code that we wrote, and and as you can see, the comments are also written with each line. Step 5 was to make PCB or fabrication so that we can actually make it compact in size. So this is just a PCB design for the prototype of a single panel that we had created, in which you can see place for ESP, for the node MCU, for the relay module, and all our components. This is an image showing the final results of our project, single panel prototype results, in which you can see a breadboard containing our four major components: the node MCU, the relay module, and the two sensors, along with an Android device showing the Android application interface of our Blink IoT. In this open circuit voltage test is being conducted. You can see 3.3 volts being read from the voltage sensor is the open circuit voltage results. Now finally, coming to the discussion section, the device that we created is basically rated for up to 100 but optimally or recommended 60 watts solar panels. Higher rated panels require higher rating of components, and thus the device can be conveniently used with 4 solar panels of 60 watt each. As a conclusion, we have successfully made a design that's IoT based and works well in conducting short circuit current and open circuit voltage tests. During our project, we realized that there is a huge scope of improvements and innovations in this field and within this project as well. So an excellent commercial device can be made with this approach if some innovations in the design as well as in the components are observed. For future directions, we would like to say that some alternative relays should be found. A design-based research should be done so that we can find an easily adjustable designs for multiple panels. And finally, ratings of components was a limiting factor for us, and thus a way to deal with this would help create a single device for any rating of solar panels. These are some references which helped us, and we are thankful to these, especially Mr. Ravi Krishnan, Herald Doshi, Blink IoT, and ResearchGate. Thank you very much. Please do visit EEC Babu pages on Facebook and YouTube. We hope that you would like this project and would like to work on this. Thank you very much.